everyone else with respect. Please use your real name on Zoom. That's required for tracking your participation. Remain muted during the presentation and workshop unless during the Q&A time. And feel free to ask your question in the Zoom chats. Also, as usual, the MedHack Discord server is a great place to follow up with questions during and even after the meeting. We are in week 3 of the workshop. So a couple of reminder, will have seminars this Saturday. Please make sure to join. And we have a very interesting topic covering deep learning. As I mentioned, will be Dr. Asner and Dr. Anne, I think, will be providing the workshop, the seminars this Saturday. As usual, we have several components, and we encourage everyone to participate in all components. Seminars that always are on Saturdays. Covers high-level research questions that have been addressed and are addressing by a top-notch researcher in medical imaging and medical side. We have always workshops that mainly cover technical concepts like the one today. These are essential for you to be able to tackle and solve problems. We have mentor tutorials where you can go and ask your question, and offline help is always available through Discord channel. I think I don't need to remind you regarding the attendance. You need to attend 70% of workshops and 50% of seminars. For those that you cannot personally attend, you can go with answering the questions that are in the unlisted YouTube link that will be shared with you after each session. For today, we have two mentors, Mohammad Nazari and Shoko Fakot. I'd like to ask you if you are available, our mentors. Feel free to unmute and introduce yourself. Mohammad, you can go first. Okay, Shokufa, if you are here, I haven't checked. Feel free to introduce yourself now.
Hello, can you hear me?
Yes.
Hello, I'm Shukufa. I've graduated from Azhar University with a bachelor's degree in computer engineering. Currently, I'm working in one of my professor's lab, focusing on developing and implementing deep learning-based models, and also their application in other fields like text and image. We also work on programming and literature reviewing of some papers and articles related to these fields. And I'm very glad that I had the chance to be one of the mentors for this week. Thank you.
Thank you, Shakufa. Mohammed, I'm not sure if you can unmute, but if you want to introduce yourself right now, feel free to go ahead. Otherwise, feel free to do it through the chat. Okay, I think Mohammed might have some internet issues. So for today...
Hi, speaking. Can you hear me now?
Oh, yeah, go ahead. I can hear you again. So Mohammed, feel free to introduce yourself through the chats. Okay, so for today, we have just Mohammed, there is a delay, I think, and it might be because of your internet speed. Feel free to introduce yourself through the chat. Thank you. The instructor for our today's session is Sebastian Ketan. Sebastian started his academic journey by attending INSA Toulouse, a 5-year French engineering school where he specialized in mathematics and data science. Sebastian has industry experience applying AI. He works on natural language processing at Airbus and Continental, and image processing at CGI. Sebastian is passionate about artificial intelligence and deep learning and is thrilled to be continuing his study at the Engel Lab at McGill University. He is now working on deep learning-based brachytherapy treatment planning. Sebastian, stage is yours.
Thank you very much, Dr. Maliki, for the introduction. So I'm going to share my screen. Can you see my screen?
Yes.
Okay, great. So this is not going to be theoretical as the previous workshop you have attended. This one is going to be much more applied, so there is going to be a lot of code. So I'm going to be talking about Tensors and Autograd, and hopefully at the end of this presentation, you will be able to answer this question: why do we need Tensors and Autograd in deep learning? I will try to answer the questions, what is a tensor and what is Autograd and how we can make use of them. So first of all, please copy this notebook. So it's available in the drive for participant, the link that I gave on the chat on week 3.2. Please copy this notebook to your own drive if you want to run it. And there is a novelty for this workshop compared to a previous one, which is we're going to use a GPU, which is a hardware accelerator for computations. And in order to do so, we need to go on the edit tab of the notebook to notebook settings, and you need to select GPU here. So I'm going to come back to this notion later, but just for you to know, if you want to have the same outputs as I have, you need this GPU accelerator setting set. So,
Sebastian, is it me losing your share the screen?
Oh, yes.
Yeah. Okay, perfect.
Can you see now?
Yeah.
Okay, so if you didn't see it earlier, you go to notebook settings, and here you choose the GPU accelerator, and you need to have this thing set up to have the same output as I will have during the workshop. So let's get to it. So now we'll first need to install some library. I don't need to install the Torch library because it's installed by default on the Google Colab notebooks. So I'm just going to run, okay, yes, I want to run. I'm just going to install a visualization library for a purpose later on my workshop, but this is just the install part. Now, what's a tensor? If you look at the Torch definition of a tensor, here you can see that it's a multi-dimensional matrix containing elements of a single data type. And there are others deep learning frameworks such as TensorFlow, Caffe, and other deep learning libraries, and they all have kind of the same definition. Here you can see TensorFlow definition. It represents a multi-dimensional array of elements. So what we can get from this is that it's an array, so just like the NumPy arrays, but it needs to contain a single data type. Now, there are two differences between NumPy arrays and Torch tensors, and there are the notions of graph and device. We will come back to this later. I will introduce what's a graph and what's a device. But just so you know, it's kind of the same thing as an NumPy array, but I like to see it as an enhanced version of an NumPy array made specifically for deep learning purposes. So yeah, so that's a tensor. Now let's import Torch library and NumPy and just print the Torch version. Here, not like any other library you could print the version of. You will see, so the version numbers. So this is version 1.11. And you will also see something else here, which is plus CUDA 113. And this thing is here because when you use Torch, you will use it with another library which is called CUDA, And you might want to check when you install and when you use Torch, you always want to check the version you're using, because some hardware are designed for specific version of libraries. So you might want to know what version of Torch you're using. Now, let's create our first tensor. So you can create a tensor by using a list of lists. And in that case, all the lists from your main list should be of the same dimension. So here we have a list of two numbers. They are float numbers. And you can print it, and you see it looks like a table. It's an array. It's basically like an NumPy array. And actually, there is a strong link between NumPy arrays that you have seen earlier in Python workshops and these Torch tensors. You can create an array from a tensor and vice versa, a tensor from an array. Here, that's what we are doing. We are creating a tensor from an array. So the numbers here that I specified are not important. Just want to show you that you can create a tensor passing as input an array. So here you see we have a tensor. Now, an interesting thing about the tensor is that, so if you use, for example, the Python built-in type function, you will see that it's a class Torch tensor. And if you call the tensor, the Torch function type over your tensor, you will see that it's another type, which is torch.longTensor. And that's because your tensor is on the CPU. We will see later on that it can be on another device. But if it is on the GPU, you will see that it's supposed to be torch.cuda.longTensor. Actually, it's always going to be the same thing, but you will just add CUDA, and this is going to be the same type. Here, the Torch documentation, please always refer to the Torch documentation. It's very rich and it's very good. It will answer all your questions about Torch. And also Pytorch forums are really good as well. Anyway, so my point was there is a specific type on the CPU, a corresponding type on the GPU, and a type of the elements contained on your tensor. So you can get the type of the elements contained on your tensor by using this dtype attribute. And here we can see that it's an integer with precision 64 bytes. Why is that? We did not specify such precision here. We only wrote integers. These are not float numbers because we did not have any point here. So these are integers, and by default, Torch is creating the tensors with the highest precision. So here, that's why you have a 64-byte precision. So that was about the types. And just so you know, you can only create tensors of numerical data, which means you cannot have a tensor of strings. Why? Because they are made to compute gradients and I mean, to do a lot of computations in general. And for that, you need a numerical data. Now, you can also, okay, let's say you want a specific type. You can specify it when you create your tensor. So with the dtype argument, here you specify the built-in float type, and it's going to give you the highest precision because you did not specify a precision for this float type. But you can now put it a float precision type. Here we put it Torch float 32. And if you print the tensor, you'll see that it's actually the default dtype. So that's why it's not printed here. But if you print the dtype, you'll see that it's indeed a Torch with precision 32 bytes, a float one with 32 bytes precision. So that was about the creation of the tensor. So here you have your tensor. Now, what can you do with it? So there are a lot of common functions that are very similar to NumPy ones, and sometimes it's just exactly the same syntax. But I just want to do a quick reminder of the common functions you can use with your Torch tensors. And yeah, I will first highlight the link between NumPy and Torch. So by using this .numpy function, you can sort of transfer your NumPy array to, your Torch tensor, because X here is a Torch tensor, you can put it into a NumPy array. So if you print it, here it's a NumPy array of type what? It's type class NumPy array. So it did do the conversion. Now let's create a NumPy array. If you want to create a tensor from this NumPy array, you can Either way, use the from NumPy function or just pass it as data argument when you create it. So there is a strong link very much between NumPy arrays and Torch tensors. Now you can use all the basic function you already know, such as getting the maximum of your array of elements, getting the minimum, the average value, standard deviation, the sum of all your elements inside your tensor, etc. You can also do any simple computation on your tensor. You can use Python built-in signs and operations. So here you can just use the plus. Here, as you only have one scalar as operand, it's gonna do an element-wise addition. So if you remind, our X tensor was 1, 2, 3, 4, 5, 6. If you add 1 to each element, you end up with this new tensor, and you see it's again a tensor. So that's the Python way of doing things. Now you can also use a Torch specific function to do the same thing, which is, for example, this add function, if you want to do an addition, and it's going to do the same thing. But if you want the results of this tensor, you need to reassign it to a new tensor. Or what you could do is do an in-place operation. What's an in-place operation is that you will directly change the results and the value, sorry, of the tensor X with the corresponding operation that you're doing here. So if you use this add underscore, you will do an in-place operation instead of doing a normal operation, and you will already modify the value of your X tensor. But you don't need to worry about in-place operation. Just you need to know that you need to reassign the value. Here I'm just printing it, so I did not do any assignment. But if you want it to have it on a tensor, you should do something like this: y=x.add. Now you can do any other operation like division, and again there is a Python operator and a Torch one, and they are doing the same thing. And you can compare as well the value between two tensors using Python operators such as equal. Here it's going to do an element-wise comparison. And you see you end up with a tensor of Boolean with a value of the equality between the two elements of the tensor at the same place. And this is equivalent to use this torch.ec function. I mean, it's doing the same thing. But let's say you want to compare two whole tensors. You do not want to compare them element-wise. You want to compare all of the elements directly. You can use the torch.equal function, and you will end up with a true if all the elements are the same, and a false if one element is not the same, at least. You can also get the shape. That's a really important point because you want to be aware of the shape of the tensors you are manipulating. So you can get this using either shape attribute or the size method of your tensor class. And here, if you remember, it was 1, 2, 3 on the first row, 4, 5, 6 on the second row. So you have 2 rows and 3 columns. That's what it's saying. There's also an interesting thing with Torch, and I mean, it's that it's broadcasting the operands you give it. You give an operation for it to match the computation you want to do. Let me explain myself. So if you have your X tensor, which is of size 2, 3, you can pass either a scalar if you want to do an element-wise computation, or you can pass a tensor with dimension 2 or 3. Why is that? Because your X tensor has dimension 2, 3. So you need to have a common dimension for your two operands. Here I'm passing tensor of shape 2, 1, and I'm able to do this computation because there is a common dimension, which is 2, and it's the number of rows. So here, if you look at it, it's going to divide the first row by 1. So it's not going to change the value on the first row. But you can notice that it turned your integers into floats because you're doing a division. But it's going to divide the second row by 2. Here you had 4, 5, 6. Now you have 2, 2.5, 3. So it's doing on its own the matching. It's going to match the dimension automatically. And you can as well pass a tensor of dimension 3, 1, and in that case, it's going to do a division on the first column. You're going to divide by 1. Here you see 1 and 4, they did not change. On the second column, you're going to divide by 2. You had a 2 and a 5, now you had 1 and 2 and 5. And on the third column, you're going to divide by 3. So just so you know, it's broadcasting the dimension so that you do not have to worry about if you want to do some operation with tensors of different dimensions. Now, something else that can be useful is you can flatten your tensor, because your tensor, they are multi-dimensional arrays, so they can have, I don't know, up to a certain number of dimension. And if you wanted them on one dimension, you can flatten them. And here we had 2 rows and 3 columns. Now we only have 1 row of 6 elements by doing this dot flatten function. You can also reshape them the way you want by using the dot reshape method. It's the same as NumPy. And just to remind you, if you use this -1, it's going to complete all the other dimensions that you're not using. So let's say you want to reshape it to dimension 2, it's going to compute automatically the remaining dimension you need to have a matching new tensor. So you had dimension 3, 2, now, 2, 3, sorry, now you're going to have dimension 3, 2. Why? Because you specify the 2 and the remaining dimensions, they are 3. So you see here is our new tensor with the new shape. You can also create new tensors from one tensor you already have by keeping the same dimension. So here I want a tensor of only zeros with the same dimension, and I have it by using this zero-like. It's really well done. And the random-like function also works if you want to create random numbers. And you can also specify directly to a random number creation the dimensions you want with rand n, and it's going to create a torch of random numbers. You can also transpose any matrix you would have, but as they can have more than 2 dimensions, you want to specify by using this transpose from the Torch API. This transpose function needs to know the dimension for which you want to transpose to. If you use this dot capital T, it's going to get as default value the first and second dimension to transpose your tensor. So you see we're getting the same result whether we're using this thing or this one. You can do what you are interested in, maybe is the matrix multiplication. So you can do them matrix-wise or element-wise. Element-wise by using this multiply Python built-in operation, or matmul function from the Torch API. And you can also use this @ sign, but I mean, it's just so you know, if you encounter it on a, let's say, a Stack Overflow looking for an answer to your question, you can encounter this sign just so you know this is a matrix multiplication. You can also put any element of your tensor to a specific power, let's say to the power of 2 or to the power of 4. It's going to do the operation element-wise. So we had 1, 2, 3, 4, 5, 6. Now we have the same numbers to the power of 2. And the same goes for any power. And what else? Yeah, I think I already covered the broadcasting. Now, something else you need to know is that a tensor has a specific space in memory to be stored, and you cannot really just assign it to a new tensor. If you do y = x, they will share the same memory, and you might or might not, but it's better not to do it because you can have errors because they share the same memory. If you want to copy a tensor, you should use this clone function made specifically by Torch to have a copy of your tensor. So it is the right way to copy a tensor. You should use this clone method and not just reassign a new tensor. You can also use this view function, but this view function is made to do different things at the same time. So it will at the same time clone your tensors. It's going to create a new tensor from the one you already have. Here it's x, but it's going to at the same time, if you specify the dimensions as argument, it's going to reshape it at the same time. So if you use view, make sure you know what you're doing because it's doing 2 operations at the same time. And there's also a tricky thing about view is that you can view it passing as argument a d type, but I do not recommend it because I mean, you need to really understand view. You can use view to reshape at the same time as clone, but I do not recommend it to cast the type of your tensors. If you want to cast to a new D type, you should use these two methods. This is the one recommended by Torch team. If you want to, let's say, put it to integers, you should use two torch.integers and the precision you want. And another function you could use is stacking, for example. I mean, I just want to show here a brief function, like main functions I think are important that you can use. So for example, this stack is going to take a list of tensors here and it's going to put them together. I mean, they have to have matching dimensions, but here it's going to create a new tensors from these two tensors. Here you see we added like one bracket. And so it's going to create a new tensor from the list of tensor you give it, and you can stack them horizontally, vertically. But I mean, so this was just an overview of the main function you can use, and I hope you noticed that they are pretty much the same, except clone, view, and two, than NumPy functions. So really, it is an array, and you can do anything you would do with NumPy, you can do it with Torch. So you might as well move now to Torch if you use only functions and libraries that are fitted to use with Torch. Now, one thing that make the Torch tensor different than NumPy arrays are the fact that we can manage them on different devices. What I mean by that is that you can have a Torch tensor on a CPU, on a GPU, on a TPU, any device you want. And here I'm going to explain very briefly what's a GPU. So a GPU, it's a graphics process unit. Here I made a small graph. This is not what this is, but this is just to give you an idea so that you understand what it's doing. So the central processing unit is supposed to execute every process on your computer, and the GPU is only made for the graphics processing. So basically, if you are using like a gaming computer, you might have a GPU on your laptop. Why? Because it's really fitted to have a good video rendering, a good quality in real time. And you can think of, so that's not what this is, but you can think of the GPU as many small CPUs in parallel that can execute very simple computations. And the fact that they can work in parallel make them very well suited for matrix computations. And that's why we use the GPU for deep learning purposes, because we do a lot of matrix computations. And now the main library you want to use when you use GPUs for deep learning is CUDA. So what's CUDA? It's something that enables you to use the GPU to do actual matrix computations, because that's not, I mean, on a gaming computer, you do not really want to do the same thing as for deep learning, for example. And CUDA is a library that allows you to increase the speed of your computation by using GPUs for matrix computations. And I will focus on CUDA GPUs. There exist other GPUs, but CUDA GPUs are the main ones. There exist as well TPUs, which are tensor processing units created by Google exclusively for AI, but they are much more expensive to rent. And also, I mean, if you can also use GPUs in parallel. So if you need more power, you can always get what you want with GPUs. So I'm going to stick to GPUs and to CUDA GPUs because they are the main ones on the market. So you can transfer any tensor to any device by using these two methods. And okay, first you need to see, do I have a GPU CUDA available on my environment that is executing my code? So you can get this information by running this torch.cuda.isAvailable function. It's going to return a Boolean, which is, I called it I have GPU, and I have GPU now. Why? Because in the notebook settings, I allowed it as a hardware accelerator. So it's going to enter this clause of my if loop. It's going to print we are using a GPU in this notebook because this Boolean has a true value. And now you can set this device variable to a string representing CUDA to put every tensor you have on the CUDA with these two device function. And a line that's really used in machine learning, deep learning codes is this line, device equal CUDA if you have Torch CUDA available, and else it's going to be CPU. So that means that it will make your code work if you have .2 device function calls afterwards. It will make your code work by just having this line of code if you're executing your code with a CPU or a GPU available. And now again, I have a GPU available on my Google Colab. There are some free GPUs on Google Colab, but if you make too much use of them, you're gonna be assigned smaller quality GPUs. So, the way Google allow GPUs is the more you use them, the less good GPUs you will have. So, if it's the first time you use them, you're gonna have a really quick GPU, and it's gonna be a good one. If you use a lot of GPU, then you will gonna have either you will wait for having a GPU, or you will have a lower quality GPU. So just so you know, you can have free GPUs using Google Cloud. And you can run this shell command. So you see it's a shell command with the exclamation point, the NVIDIA SME to have more information about your GPU. So here you can just know what GPU am I using right now. It's a Tesla T4. I'm using 0% of its capabilities. Why? Because I'm not doing any computation at the moment. But this is just so you know, you can run this command while running a program having a GPU accelerator set to get the utilization of your GPU. Now, you can, when you create a tensor, so let's just create a tensor of ones with size 2, 4, you can specify the device you want it on. So here I specify the device, which is set to the string CUDA. So I specify CUDA as the device. And now if I print the attribute of the tensor I just created, I can get its device. So here you see it's CUDA semicolon 0. Why? Because you can have many GPUs working in parallel for same program. So you can have CUDA 1, CUDA 2, etc. So here I only have one CUDA GPU available, so it's going to be CUDA 0. I hope I'm not going too fast. If not, you can ask a question on the chat, and maybe Farad can help you, or the mentors can help you answer them. Something you have to know is that you want to be aware of where your tensor are stored. If some are on the GPU and some other are on the CPU, you might not be able to do operations between them. And you're going to end up with an error saying that it expects all the tensor to be on the same device. It makes sense, right? Because you need both tensors, of the operation to do the operation. And so you might find operations that are available between tensors on two different devices. But in that case, I would recommend just having your two tensors on the same device. You can learn more about it by reading this Torch discussion on operation on two different devices. But in general, just know that you want all your tensor to be on the same device, and it goes as well for your network. If you create a neural network, you want it to be on the same device as the tensor you feed it as input to do the computations. Because otherwise you would add an extra step, which is transferring tensors to the same device before doing the computation. So yeah, you want them to be on the same device. That's what I'm saying. And yes, when you're moving a tensor to a specific device, you need to reassign it. But you do not need to reassign it if you work with Torch NN modules. That's something you will see later on, but just so you know, you do not need to reassign it with neural network modules. You need to reassign it with tensors. So if I'm doing tensor.cpu, by the way, it's equivalent to torch.2 CPU. If I'm doing this is not going to move my tensor. I need to reassign it. Here you see it's if I print the device after calling this .cpu, it's still CUDA. Why? Because I did not reassign it using, for example, tensor equal tensor .device. So just so you know, you need to reassign them. And yes, here I reassigned it and I print the device afterwards. It's indeed CPU. And if I put it on the CUDA and then I reassign it as well and I print the device again, it's going to be on CUDA. So you can very easily transfer a tensor from one device to another. And after there are some functions that allow you to get the content of a tensor, but some of them might do some implicit transfer that you might not be aware of. So for example, if you use this dot item to get the data component of your tensor, here first item only works with scalar value, so you need to get a tensor with the scalar. So here I got 2 index from my tensor, which was of size 2 times 3. So this tensor is 1 scalar, and I can call the dot item to get the data from this scalar. But this item function is going to put implicitly my tensor to the CPU. And that's something you should be aware of, especially when you create a for loop to train any neural network. Because if you call such a function a certain number of times inside your loop, you will have many transfers that you're not aware of happening. And well, that's just something you want to be aware of. Some function they call implicitly transfers to the CPU, such as the .numpy. You can call the .numpy as seen earlier to transfer it to a numpy array. But if you call this, you will need your data to be on the CPU. So first you need to call .cpu before calling the .numpy. And in general, there is a CUDA documentation page on the Torch documentation that explains really well what I just explained you. I mean, it's pretty much the same thing, but it's there are other things as well, and it's really interesting. So do not hesitate each time to go see the Torch documentation. It's really great. And yeah, okay. So there's another thing is your CPU and GPU. There are 2 different hardwares, and they can do things asynchronously, which means you can have a set of lines on your code that are iterative. So, I mean, each line is one after another, but the computation, if they are done on the CPU and on the GPU, they can be executed at the same time while there are 2 different lines on your code. And that's something you need to understand, is that you are dealing with 2 hardwares and they can be operating at the same time. So if you want to, let's say, time your loop, your training loops with a timer, you need to be sure that they are the CPU and the GPU, they are synchronized before and after timing your loop. Why? Because sometimes you can wait for the results of a tensor, because in your training loop you might change the value of a tensor. You might want to wait for the results of this tensor before getting the final or start time. So that, I mean, it does not really matter if you do not remind this, but just so you know. And again, you might wonder, okay, how efficient is a GPU compared to a CPU? What, do I really need a GPU to train my model? And well, if you have a really small model, it might not impact that much your training time. But if you have a normal model, or even better, a big one, it's gonna get you a very, very big increase in your training time. Your speed is gonna increase a lot. So here I put as a link another Google Colab that's using TensorFlow, not Torch, and it's doing like very simple computations. So you have one layer and you do the operation in a loop. And just so you know, if you do the same computation, you can have like a 35 times gain in the speed using the GPU compared to the CPU. And this is just a small example, but you can imagine that the gain in time is very much, I mean, it's much bigger if you have bigger models and a lot more computations to do. So yes, GPUs are more efficient for deep learning training in general, and it's even more true when you have big models, big data, and yes, so you want to use GPUs when you can. Now, okay, so we have seen 2 of the arguments, 3 actually, of the arguments of the Torch.tensor function. So the data you feed it with to create your tensor, the D type you can use, and the device, if you want to set it or not. Now, there are two other arguments from this Torch.tensor class, which are pin memory and requires grad. I'm going to go for the easiest one to explain first. So what's the pin memory? It consists of putting the CPU, putting the tensor from your CPU in a specific place that is easily reached by CUDA to transfer it to the GPU. So basically, you want to be aware of this pin memory argument only when you plan on using the GPU, and doing some transfers. And it's really well explained by the NVIDIA documentation. So I'm not sure I explain what NVIDIA is, but NVIDIA is the main provider of the GPUs. And of course, they do CUDA available GPUs. They are the main GPU provider on the market. And here they explain that your GPU can only access data from the non-pageable memory of your CPU, and that's why you need to pin this memory. If you do not pin your tensor to this specific area of your CPU, then your transfer is going to take a bit longer. I mean, it's not a huge difference, but you need to have this operation done before you can transfer it. So you need to put it from the pageable to non-pageable memory for it to give it to the GPU. That's not really important, but just so you know, pin memory can accelerate your data transfer between CPU and GPU. And also looking at the data loader class that you might encounter later on during the next workshop, they also have this pin memory argument. Where is it? It's here, that you can set to true if you want the data to be on this specific location on the CPU, this non-pageable memory. So just so you know, you can use it through the data loader as well, but I'm not going to present the data loader here on this workshop. So now coming back to Torch tensors, there is a last argument, which is maybe the most interesting ones and which is going to lead us to Torch Autograd. It's the requires grad argument. So by default here, you see it was set to false. So if you do not set it on your code, it's going to be set to false. Now you can set it and put it to true on your code. And I'm going to show you now what it's doing. So if you set it to true, the Torch.Autograd API is going to record the operations that you're doing with the tensor for later gradient computations. So now I'm going to present Autograd. So what's Autograd? It's, again, the documentation is pretty rich on this, but it's a tool that is automatically differentiating the tensor. So it's going to automatically compute the gradients that you need for your deep learning training. And it's it's something really, it's incredible, because the gradient computation you would need to do if you were going to do it manually while training your neural network, they are really, really heavy. And this Autograd is going to do everything for you. And that's what I want you to understand. What Autograd is doing, it's computing the gradients from the tensor operation you are doing on your deep neural network training. And just something you know is that if you want to require the gradient, you need numerical data that's not integers. You need floating points. Why? Because when you compute some gradients, you might have to do some division, some multiplication, and I guess that's why Torch tensor is only created right now. Maybe in the future it's going to change, but right now you can only require the gradients with floating points tensors. And you might encounter while Googling the variable class on a Torch code, and you would see that it's coming directly from Torch Autograd API. This was the old way of creating a tensor for which we want the gradients. But now variable is depreciated, and now it's all about tensors. So if you see it, just know that it's the same thing as a Torch tensor right now. This was just the old way of doing things. But you can see it that it's a tensor, but we also see something else, which is here, the requires grad set to true. So just, yes. Okay, I don't know what this text cell is doing here, but that's not the point. So you can, if you try to set a tensor and to require its gradient, but this tensor actually contains integers data, it's gonna give you an error. Why? Because as I explained, you can only require the gradients with the floating point tensors. And if you see here, the text that is printed is this one, because this first try clause gave us an error, so it went to the except clause of the Python code. And now it works. I mean, this creation of tensor works while requesting the gradients. Why? Because I specified directly the data type that I want, and it's a floating point data type. So it's working. And after that, I can print the requires grad attribute from the tensor I just created. And you can see that it is set to true. Why? Because I set it here to true. So it's that simple. And you can access the value of the require grad attribute of a tensor by just using this dot requires grad thing. Now let's create a tensor for which we do not require the gradients. We can change this setting afterwards. So here you see we are creating a tensor. We are not specifying to request the gradients, but if you print the value of the attribute is set to false, but you can change it afterwards. So if you do not set the gradient request on the tensor creation, you can still change it afterwards. So here you can just use the requires grad underscore function and set it to true. I think there are other ways to change the gradients requirements attributes, but this one is a good one as well. So you can just change the value of the grad requirements and put it to true or false in the program. You do not have to recreate a tensor to do that. And if you see here, after changing the value of the gradient requirements, now it's set to true and not to false anymore. So, okay, so we can specify that we want to require the gradients. Now I want to show you how you can use it. So we're going to do some simple computations and show you how it works, how Autograd works. So let's come back to our X tensor. So X, what is X in that case? It's a tensor of value 5. So X is 5. I just do a simple computation. I add 2. So it makes a Y with the value of 7, right? So if you print it, you will have the value of 7 here. And it's a float. Why? Because X was a float as well. What's interesting here is that you created your X while using this require grad argument. And if you print Y, which is the result of a computation with your tensor X, for which you require the gradients, if you print it, you will see that you have something else that appeared here, which is a gradient function. What is that? It's just keeping track of what you did with your tensor. So here, the last thing you did was an addition, and that's why you have this add gradient function. And this backward thing is specified because when you are going to do the backward propagation for the gradient computation later on, this is what's going to be used. This is the gradient function. And actually, all the gradient function, they are recorded. And it's building some sort of graph. So I'm going to present a graph later on. But just so you know, if you create a tensor while requiring the gradients, it's going to eat up more memory than a normal tensor for which you do not require the gradients, because in this same memory storage, you will have at the same time the data that is contained on the tensor and all the graph and gradients associated to this tensor. So that's important for you to know. The memory that you're going to consume while using a tensor and requiring the gradients is higher than the memory you would use by using a simple tensor that do not require the gradients. Okay, so now, yes, and you see, so here we did not specify that we wanted the gradients for Y, but it's still computing it. So the value of requires grad attribute is set to true. You can also do the computation inside of what we call a context manager. So with the with clause in Python, and Torch has many context managers that can make your code more readable and easy. I mean, it's going to make things more easy for you if you use these context managers. So here, what does it mean is that inside this with clause, all the computations that I do not want to keep track of the gradients. So here, if I create another tensor from the same X tensor and I print its required grad attribute, it's going to be false. Why? Because I'm inside this context manager that is saying that I do not want to record or to track any gradients. So just so you know, you can do a lot of things, but it's very flexible with the Torch API. It's really a great tool to work on. And yes, you can access the grad function that you see here by just calling the grad function attribute. Now, as I want to show you a graph, I'm going to add another computation here because I want to show you something, I mean, at least a bit complicated. So here, I'm going to create another tensor, which is going to be W. And for W, I want to require the gradients as well. And then I'm going to do another operation with Y and W, and I'm going to put the results into Z. Okay, you know what, this line is not useful. It's because before I did it on more than one dimension, so I needed to have one scalar at the end to compute the gradients, so that's why. But I mean, okay, let's just put it into an output value. So you do another operation on a new tensor you just created. Let's run this. So now you will see that again, the last operation is, yes. Did someone say something? Sorry. No. Okay. Is there something on the chat? I don't see the chat actually. Anyway, so I'm gonna have some time for question at the end. Don't worry. So we're just doing another computation, and the last one that is taken into consideration here regarding your grad function is the plus, so it's the addition. Why? Because it's the one that put together two different tensors. So you have here an output which is made of many tensors for which you require the gradients. And yes, there is a tutorial again on Torch Autograd. By the way, I've been using a lot of Torch documentation to build this workshop from scratch, but here they are explaining a lot of things on the gradients, but I'm going to explain them here as well. So an important thing to notice is that if you want to access the gradients, you can just use .grad and you will get the attribute gradient from the tensor. But if you try to get it before calling this backward function, they are going to be set to none. Why? Because as simply as it is, this backward function is going to compute the gradients for all the leaves tensor of your graph. I'm going to come back to this leaf function later on, but just so you know, you will not have gradients before calling this .backward function. Here, after calling out .backward, I now have a gradient value for my W and for my X. And actually, this is something you could have computed yourself. So I'm just giving a small example here. So this was my function at first. And if you want to get the partial derivative from this output to X with respect to X, this is going to be, I mean, you just remember your derivative computation. This is one-dimensional, so this is really easy. If you want to derive by X, this is just going to give you 3 because you have 3 by X. This is the only thing here dependent on X. So that's really simple. And the W, if you want the partial derivative by W, this is just 1 times W. So at the end, it's just 1. The gradients you get by deriving by W with respect to W. So, but this is like a really dummy case, and we will come back later to the use with neural network layers. So now we can wonder would it have worked with y? Because we also created this tensor from other tensors. So can I get the gradients with respect to y? And here you could compute it. It would give you 3, right? But the gradients, okay, let's just try to print the gradients of y. They should have been computed by using this dot backward function. Why they were not computed, it's explained on the user warning you get. So first you can see that the value of the gradient is set to none. And it's explained that here that y is not a leaf on the graph. And what does it mean is that if you wanted it to be a leaf, we can do that again here. So what we're going to do is this. We're going to create a new tensor from, I mean, it's going to be the same computation. The only thing that is different here is that we're going to set the requires gradient to true. I'm just going to run that. And I'm going to run as well the X cell to create it. And where am I right now? Yes, I'm gonna run some cell again. And now, so I did the backward pass. And the first thing you notice here is that there is no more gradient for X. And you can wonder why? Why? Because I required the gradients when I created X. Yes, but what you also did is created the Y tensor from the X tensor, and this one is going to require the gradients. And so when you call this require grad argument, you're going to build the leaf of your graph. And I'm going to show you a graph. It's going to make things pretty much easier. But here, so X has no more gradients, but if you print the Y gradients, it's going to be 3, the ones you computed here. So I'm going to print the gradients for both cases so that you understand. And now, yes, okay, something you could think of is computing the gradients of the output value, the output tensor, but I mean, this has not really a point. You would just do the partial derivative of out value with respect to out. I mean, this is one, but I mean, you have no point getting this gradient, so, and it's not a leaf of the graph. Anyway, so now let's just show you a graph. What does it look like? So if you use the torch.vis library I installed earlier, you can print the graph that led to the creation of your tensor. So here, what do I have? This was my Y. So Y, where are you? Y, and you can see it as well with the dimensions. So here is Y is made of X, which is like a 2-dimensional, is 1, 1. And my W has only have 1 bracket, so I just put it this here so that you understand better which one is which. So this one is Y, this one is W. You're going to multiply Y by 3, and then you're going to sum Y and W. I mean, and W times 3 to obtain your output. So this is the graph that led to the output value. And here you can see that there is no X value. X was before, and we did not require gradients for X. Now, let's just come back to what we did earlier to show you the differences in the graph. So let's just recreate X, Y, W, and output tensors. So here again, we have no gradients before calling the backward function. After calling the backward function, we have the gradients. And here we do not have the gradients for Y. And you're going to understand everything by looking at this new graph that was created. What is that? So we added another step here, which is, so now this tensor is X, is not Y anymore. And you can see it by just looking at this new operation that is on the graph, which is add backward. This was, if you remember, the X plus 2 that led to the Y. And yes, so just want you to understand what's a leaf of the graph. So basically, when you're going to train a neural network, the thing you want to compute the gradients from are the weights and biases of your different layers. So the leaves of your graph are going to be the weights and biases. And we're going to come back to this really soon. Yes, so I explained, so you see here, there is a whole graph that comes with the output value. You can, if you want, just get the data value from this tensor that has right now all the data gradients and operations stored on memory. But you can only get the data from it by just detaching the graph from it, right? So this detach function is gonna get rid of this whole graph and just keeping the data value from your output value. So if you create G2, which is another graph, okay, I'm calling the make dot function here as well, but I'm calling it on out.detach and not out anymore. Here, if you create another graph, you will see that, oh, there is no more operations or leaves or anything. I just got rid of the graph that led to the output. So just to show you, the detach function is going to get rid of the graph. And basically, you are going to come back from a torch definition like this to like a simple torch definition as we did in the beginning, where you do not require the gradients. So just to keep the data from your tensor. And yes, of course, if you want to clone it, if you want to copy the tensor, if you just call clone on your tensor and you're going to copy the tensor, the whole tensor is going to be copied, which means the data stored in the tensor, the graph associated to the tensor, the gradients, everything. So here, the copy of X, which is the second line, copy tensor. You see here we have a tensor, copy tensor here is a tensor, but it does not only have the data, it also have the gradient functions that were on Z in the first place. So these two things, they are the same. Now, if you clone a tensor after detaching the graph, your data tensor, so the third thing that I print here, is only containing the data part of my tensor. And so it's lighter in memory and it's more to the point if you want only the data and not everything else that is on the tensor. And again, yes.
We had a comment regarding the pace. I think this might be a little bit, since it's a new concept and it's a little bit complex. I think if you can repeat this process and slow down the pace a little bit so audience can comprehend that.
Yes, okay, sorry.
Perfect, thank you.
So let's just go back to where we were. So the first thing we did was create a tensor. And then we do an operation on this tensor. We just add, let's say, a number, or we do multiplication or division. So we are building operations from this tensor. And each operation we are doing, they are going to be stored somewhere inside the graph of the tensor that I created. Why it's going to be stored? Because I specifically asked the automatic differentiation library of Torch to keep track of every computation I do with this tensor. So because I set this requires grad argument to true, Torch is going to record everything that I do with this tensor. So this X, if I do X plus 2 and I create Y, and then from this Y, I again create a new tensor, which is called output here from Y and W, every computation that I make here is going to be stored on the graph of the tensor. And so that's what I was talking about memory consumption. You're going to consume more memory if you store the whole graph and the data than if you just store the data. That makes sense, right? Because you have more information to store. And if you, yes, and after that, so once you have done your computation, if you call dot backward function on the last output of all your computations, the automatic differentiation tool of Torch is going to compute the gradients for all the tensor that were used in the creation of your output value. Here is going to compute the gradients for each one of these tensors. And what are the gradients? Here we are one-dimensional. We only have one dimension, so it's just the derivative with respect to each one of the tensors I used. So if you take the derivative of the output value with respect to X, here you have the whole computation written up. So here, the only thing that is dependent on X is 3 times X. If you derive this by X, you're going to end up with 3. So that's the value of the gradients you get here. And the same thing goes for Y and X. So, but I mean, I'm going to give another example. So if you did not understand this at first, you will understand it later. And just so you know, you can get rid of the graph that is stored on your tensor by using this detach function. So that means your tensor here out is storing both data and graph. Out.detach is storing only the data. Okay, now let's just have a look at this video that is provided on the Torch tutorial for backpropagation. I just want to show you a brief explanation on the video. Okay, this is an ad, sorry. So this is a YouTube channel that explains everything with animation. I just want to show you what you want to do when you want to upgrade the weights and biases of your network. So what you have is you have a series of computations, and I think Hunter in the previous workshop, he introduced you to activation function. So after each layer, you add another function, which is an activation function. And so here, the activation function is the sigma, and the Z is the output of your layer. So you have the weights and biases as well as the input of your layer. And after that, you do the sigma function on this output. Okay, let's just show you the video.
Are you uncomfortable with the relevant calculus and how sensitive the cost function is to these variables?
Okay. So I'm just summing up what he said earlier. So what you want to do is to know how sensitive your loss function, when you train your network, you're trying to reduce some loss. What is the loss? It's the difference. I mean, it's a function that computes some sort of difference between the target and the output of your network. And what you want to do during your training is to reduce this loss. And this loss, it's a function of the output of your network and the target. And the output of your network it's a function of all the layers of your network. So let's just have a look at this video, a small part of it, to explain why you want to keep track of the gradients and bias in a neural network training.
It's going to cause the most efficient decrease to the cost function.
The cost function here is the loss function, sorry.
And we're just going to focus on the connection between the last two neurons. Let's label the activation of that last neuron with a superscript L, indicating which layer it's in. So the activation of the previous neuron is AL-1. These are not exponents, they're just a way of indexing what we're talking about, since I want to save subscripts for different indices later on. Now let's say that the value we want this last activation to be for a given training example is Y. For example, Y might be 0 or 1. So the cost of this simple network for a single training example is AL minus Y squared. We'll denote the cost of that one training example as C0. As a reminder, this last activation is determined by a weight, which I'm going to call WL, times the previous neuron's activation, plus some bias, which I'll call BL. And then you pump that through some special nonlinear function like the sigmoid or a radian. It's actually going to make things easier for us if we give a special name to this weighted sum, like Z, with the same superscript as the relevant activations. So this is a lot of terms, and a way that you might conceptualize it is that the weight, the previous action, and the bias all together are used to compute Z, which in turn lets us compute A, which finally, along with the constant Y, lets us compute the cost. And of course, AL-1 is influenced by its own weight and bias and such. But we're not going to focus on that right now. Now, all of these are just numbers, right? And it can be nice to think of each one as having its own little number line. Our first goal is to understand how sensitive the cost function is to small changes in our weight, WL. Or phrased differently, what is the derivative of C with respect to WL? When you see this del W term, think of it as meaning some tiny nudge to W, like a change by 0.01. And think of this del C term as meaning whatever the resulting nudge to the cost is. What we want is their ratio. Conceptually, this tiny nudge to WL causes some nudge to ZL, which in turn causes some nudge to AL, which directly influences the cost. So we break things up by first looking at the ratio of a tiny change to ZL to this tiny change W. That is the derivative of ZL with respect to WL. Likewise, you then consider the ratio of the change to AL to the tiny change in ZL that caused it, as well as the ratio between the final nudge to C and this intermediate nudge to AL. This right here is the chain rule, where multiplying together these three ratios gives us the sensitivity of C to small changes in WL. So on screen right now, there's kind of a lot of symbols, and take a moment to just make sure it's clear what they all are.
So I just want to show you this small part of this video because I think it's really well done. The animations, they are great. Just to show you that so you will have a loss function that you want to minimize. And what are the gradients? They are the importance of a specific weight or bias on your output. And that's why you want to compute the gradients in the first place. But feel free to look at this video. It's really well done, and it's going to explain what backpropagation is. And so, I mean, it better explain it than I would, so that's why I wanted to show you, but feel free to look at it fully later on. Okay, I cannot go back, yes. Okay, so I hope this video will help you understand why you need the gradients. I'm just going to show you another example of Pytorch tutorial with Autograd to compute the gradients. So here you have two tensors, and you just do operations on them. And just so you know how to compute the derivative, here a to the power 3, the derivative with respect to a is going to be 3 times a to the power of 2. And if you just look at the value of the gradients, are they the same? If you do the computation on the derivative, yes, they are the same. So just to make you understand that all the computation that are made under the hood by Pytorch, when you use this backward function, these are computation that you can make yourself. It's just that the amount of computation required for training a neural network, it's really huge. You cannot imagine to compute all of them manually, especially when you're dealing with matrix, because here we are only doing it with small dimensions, like one-dimensional data. But the Autograd API from Pytorch is going to do all the difficult gradient computation for you. And that's something you want to understand, is just this dot backward function is going to compute the gradients. And you will use them later on to update the weights and biases of your layers of your network. But yes, that's all. And now a final thing that I wanted to show you is using it with an actual neural network layer. So let's just create a layer. Here I'm getting the really simple linear layer. And if you have a look at the documentation, it's just gonna do like a simple multiplication and then add the biases. And from the arguments, I take an input of size 1 and I want an output of size 1. So really, I don't want any matrix because I want to be able to compute the gradients and to show you how it works. I just want you to know that when you use Torch neural networks modules, they also have gradients. It's not a Torch tensor, it's a Torch module, but they also have gradients. And you can, so after creating this linear layer, if I want to access the weights and biases, I can just call the weights and biases attributes. And here you can see that this is my weights and this is my bias, and they are random. I mean, you can have a look on the documentation on how they are initialized, but you can set them. I actually want to set them because I want to do some simple computation. So I will set them. Here you can set them by just going to the data attribute on the layer, and you can set them. And after you can print them again, and you will see that the value, they have changed. And now let's create an input for this linear layer. My input is going to be A, and A again is going to be a simple number. Now let's get an activation function after your layer. So the activation function, they are the functions that are going to make your computation non-linear inside your neural network, and it's going to make it able to learn more difficult features than just if you were just using linear layers. and linear computations. So that's why the activation function they are used for. Now let's just create the output of my linear layer, taking as input my A, which is here. So what it's going to do, it's going to do A multiplied by the weights, and it's going to add the biases, just as described here in the documentation. So I'm just going to do a simple multiplication and then a simple addition. Now, next step is using the activation function over the output of my linear layer. And this is going to give me another input, which is going to be capital Y. So I chose TANH activation function. I could have chosen any other ones. If you want to have the formula, it's here. And so, I mean, it's a formula with exponential, so you can easily compute the derivative from this formula. So that's why I chose it in the first place. And then again, in the same way as for the tensor, if you did not call the backward function, you have no gradients for the weights and biases. So if you print them, they're going to be set to none. Now let's call the backward pass on the Y output here, the capital Y output, and let's just call again the gradient attribute of these layers. And here they are computed because they have been computed. So the gradients, they are computed when you call the backward function here on the output. And the output on your neural network training is going to be the loss, because you want you want to know how the gradients and weights, how the weight and biases that are set at the moment, how do they impact your loss? And that's how you're going to update them later on. So here I was able to compute gradients for weights and biases of one layer. Could I do it on myself? The answer is yes. Why? Because it's really simple. It's one-dimensional, and I know all the computation that are made. So the derivative of TANH is this one. So just to let you know, I can compute everything. So with a simple derivative formula that I explained here, I can come back to the same outputs, because I know how the gradients they are computed. You just have to know some derivative formulas, and then you can compute them yourself. But we will see here that, so here it was kind of simple. I mean, you just take the formula and you do the derivative, and then you do the computation. So it's kind of easy, but it's become harder and harder when you add layers on top of each other. So let's just now do a try by using two layers. Oh, sorry. So here I create one layer and a second one. I set the bias and weights for each of them. I choose two activation function, which are going to be two sigmoids. You can have an inch of what is the sigmoid here. And then, so your input is going to pass through the first layer, then the activation, the first activation, then the output of this first activation is going to go as input to the second linear layer. And again, it's going to pass through a second activation. That's what is happening when you're training, when you're doing the forward pass, basically. When you're passing your input through your model, it's going to pass through different layers and different activations. And then I call the backward pass, and I can print the gradients that have been computed. And if you want to have a look at the graph, what does it look like? So I have two layers. Each one has one weights and one bias. So this is the weights and bias of the first layer. This is the weights of the second layer and the bias of the second layer as well. So this is the graph that comes with capital Y. So capital Y is my output. And so you see all the computation that have been recorded on the graph. And you can compute the gradients by just a simple line using this dot backward pass. Now, what about you try to compute them yourself? Well, so I did it. It's doable. And in fact, it's doable for any neural network you would do. It's just very cumbersome, and you do not want to do it yourself because it's a lot of computations and you have a lot of derivative to compute. But this is something you could do. You can compute everything yourself. And you see here, I get all the same values for my gradients as I got using the dot backward function. The gradients that I got from the backward function are the same that the gradients I got here by just computing them manually. And that's what I wanted to show you, is that you can compute everything manually, but it's just super difficult if you have a big neural network and super long. So you don't want to do it yourself. That's why Autograd is for. It's going to compute all the gradients on itself. And just one last thing is, when we talk about backpropagation, why do we talk about backpropagation? Because if you compute the gradients for this first leaf of the graph, you're going to compute the gradients for regarding this first operation. And this first operation is also going to be used to compute the gradients for the next thing you want to maybe update its value of. So the weights here. So here it's very simply shown here. So the gradients of the second bias here, it's a very small computation because there is only one operation. And you reuse the same thing. So here you see it's the same code here. You reuse the same thing and you add on something else to compute the gradients of, here it's the bias. So you use this and you add this operation to compute the gradients of the weights. And that's how you backpropagate through your layers. So I'm not going to go through all the computation. Please feel free to have a look at them. But just to show you, you can compute the gradients yourself. It's just super long and difficult. So you do not want to do this yourself. You just call the dot backward function, and it's going to work both on tensors and on neural network modules from the Torch library. Yes, so you could imagine doing the same thing with a convolutional layer. It's just that you're gonna maybe have a matrix if you're gonna do a convolutional 2D, but I mean, it's doable. Everything is doable. You just have to take a pen and compute the derivative. But everything is also doable just using the dot backward pass. And I'm just gonna do a small link with the next workshop you're gonna have. So the loops that will be your training loops, they will always look a bit the same. I mean, when you use Pytorch, so you're always gonna loop through the different epoch. So what's an epoch? It's just that you're gonna loop through all the samples in your data sets. And then you're gonna go through each data sample of your data set. They can be packed into what we call batch sizes. So it's gonna take samples at a time of a specific batch size. So you can take, let's say, 2 samples at a time. That means you have a batch size of 2. So you're gonna have what we call a data loader. This is something that is gonna give you the data. So here in the data thing, you have both an input and a ground truth. The ground truth is the target. So here we are on a supervised setting. This is the Pytorch classifier tutorial. So we know the ground truth, and we have as well the inputs, and we want to approximate a function that links the input to the output. So we get the data, we set all the gradients to 0. Then our input is gonna pass through the network. This is gonna give us an output. From this output might not look like the ground truth that I want in the first loops of my training, but later on it's gonna get closer to it. So we're gonna get this output and compute a loss between the output and the ground truth. And after that, we're gonna compute the gradients on this loss with respect to all the weights and biases of our neural network. And this backward line, I hope now you understand what it's doing. It's just computing the gradients. Now this optimizer step, this is how we update the weights and biases. I will leave that for next workshops. But yeah, so I hope you understand now what is doing this backward function. You're gonna find it on any training you're gonna do with Torch API. And yes, so I hope I made that clear. This is just gonna compute all the gradients, and for this is gonna get the results of all the computations you're doing with inside your network. And yes, after that, there are some other resources that I put if you want further knowledge. So, but I'm not gonna cover them today because I think it was already a lot. But just so you know, you can, I mean, it's very flexible with the Torch API. You can do a lot of things. And and you can freeze or the gradients or add them. You can do a lot of things. It's very flexible. You just have to have a look at the documentation. Please go to the documentation. All your answers will be there, as well as the Pytorch forums. They are really good. A lot of questions are answered there. And yes, so these are extra resources if you want to go through them. But I hope I made it clear that just what is doing the backward pass here is computing the gradients with respect to each weights and biases that are making your network. So I hope it was not too much. I will be happy now to answer any question or anything was unclear. Please do ask a question on the chat, or you can even unmute if you want to ask some question.
Thank you. Now we have time to go to questions. Feel free to raise your hands, your virtual hand on Zoom, and I can ask you to unmute. Also, Zoom chat is another option. So before people start typing their question, I want to ask you just for the point of practicality. So as you mentioned, Autograd really it's behaved like an engine that's calculate all of this complex computation behind the scene. So does someone need to know about the nitty-gritty of the Autograd to be able to use a machine learning or train a model?
So yeah, that's a very good question. No, of course, no, you don't need to know what everything is happening under the hood. You just need to know that this Autograd thing is computing the gradients for you. It's doing all the difficult computation that you would not do yourself, is doing on itself. But you do not need to understand everything that's happening on Autograd. You can, if you want to have a look at the documentation to see how it's implemented, because Torch is open source. It's a C++ background. So if you know a bit of C++, you can have a look at it, but you do not need to understand everything that's happening under the hood.
Yeah, great. However, I like to highlight here that some of the content covered here really help you to find out if you faced with some bug in your code. It helps you to find out why this bug is happening, and that would be really valuable.
Yes, there is a lot of help on the internet. Please Google, ask for your error. You can basically copy paste. I don't know if you noticed, but when you have an error on a Google Colab, let me just look for an error. You can, yeah, okay, there is already a link to Stack Overflow, so it's gonna create the web search for you, and you can go through Stack Overflow. They have a lot of answers there, and you can directly ask your question if you want to, if it is not already answered. If you have trouble with your code, but most of the question you will have, they have already been answered either on the Pytorch forums or on Stack Overflow, and they will be answered or explained on the Pytorch documentation.
There's a question on the chat. Is Autograd equivalent to TensorFlow's Adam, SGD, etc.?
So no, this is not equivalent. And okay, so first there is Torch. Torch it's a deep learning framework. This is the one we use today. And there is TensorFlow. TensorFlow, this is another deep learning framework. This is another deep learning library. It's pretty much doing the same thing. I mean, you might prefer one or the other, but so Torch, it's a library. TensorFlow, it's another library. Autograd, it's a tool for computing the gradients. Adam, stochastic gradient descent, etc. They are algorithms to update the weights. I mean, to update your weights and biases in your network regarding the gradients you computed with Autograd. So Adam, stochastic gradient descent, they are optimizers. And this is maybe the next step that you're gonna see on next workshop. And I didn't mean to overstep this workshop because it was already a lot, but here you have an optimizer, and this is your Adam optimizer or stochastic gradient descent. And some optimizer, they might require only the gradients to compute the updates, but some might also need the gradients and the moments of the gradients, so first and second derivatives, such as Adam, and it's gonna consume also more memory if you want to store more things on your tensors. So just, yeah, optimizer, it's something else that is using Autograd because it's using the gradients that are computed with Autograd.
So we'll have a more to come about those concepts. You will be learning for those in the future workshop. So it might be overwhelming right now. You might see or hear many different words that perhaps doesn't make sense at this point for you, but they will come to the big picture down the road in the future workshops.
Exactly.
So any other questions?
When do we start converting data to tensor format? That's a good question. So, I mean, if you only work with data exploration and you want to get a hint on what store your data when you want what you want to do with it, you do not necessarily need Torch tensors, but you need Torch tensors if you want to train a neural network, because you will need to compute some gradients and to update the weights and biases of your networks with regard to these gradients. So I would say you need to convert them to tensor, convert your data to tensor when you're going to do a training with Torch or with TensorFlow. Yes, please.
On that note, you will see a complete pipeline for training a model. During that, the data will build a pipeline based on that. Usually a dataset class will read the data, and at the end, you pass this data to the training pipeline, and there that data will be converted to tensor. And you see that when we cover the complete pipeline, you see how these components come and fit together. Yeah, it's definitely you need to read the data. This data might be images, it might be a text or other formats. However, most of the work that we do during this summer school is focused on images. So you need to read the images. When you read that, usually it will be a NumPy array, and you need to apply some transformation on it. More on that in the future sessions. And at some point before feeding them to the model, you will actually need to transform them. And what is model? Again, you will be having sessions that tell you how to build a model from scratch by stacking different layers. Which layers will be stacked? What's the responsibility and duty of them? So those are things that you will see down the road. But it is really important to right now, as Sebastian suggested, make sure to do to follow the different links provided, read about these concepts in the documentation for Pytorch. It's a really rich environment with many users that make it really easy to learn and search for new concept. And if you face an error, copy paste the error message, and that's usually the best way to find out what's the cause of this error and how people solve it, so you can easily solve those.
Yes, thank you. So there is another question on the chat. When we want to operations on GPUs? So I understand the question is, when do you want your operation to be done on the GPUs? So as I tried to explain, so if you are doing like really simple computations that, like, let's just say an addition, you will not see a big improvement if you do your computations on the GPU compared to the CPU. But when you train a neural network, you're going to do many matrix operations, and it's going to be done inside a loop. So you're going to be doing them many times, and you will see that at the end, you will observe a very big improvement in speed training using the GPUs. So the GPUs, they need to be used when you have a model that's big enough. So when you do at least many operations on your data. And but I mean, you can try it. Just do your operations with the CPU and the GPU the first time, like not in a loop, time it, just see how long does it take. And then you will see an improvement on the GPU most likely. And then it will be faster if you use the GPU on the training.
So once again, the success of or the value of GPU to deep learning is due to the fact that many of the works and operation that we have for models is matrix operation, and GPUs really accelerate those kind of operations. This is, first of all, there are cases you might not have GPU. So if you run this model on a device, more specifically, not in the trainings, most often when you deploy this model on a device, that device might not have GPU. Of course, in that case, you need to run it on CPU. But if you have GPU, training models on GPU accelerated sometimes to, depends on the characteristic of system, but 100 times sometimes faster. So that would be really helpful for training and working with models, because your waiting time before seeing any result and improvements will be decreased by a huge factor. If possible, for training deep learning model, we always use GPU if possible, or TPU in case you have access. But if not, you might be able to train a model with a small CPU on a laptop as well. But when we go to larger scale model, that process is really slow. But the nice thing is that Google Colab gives you free GPU and also TPU that you can use. Okay, perfect. I don't see any other question on the chat. I think we can conclude the session at this point. Is there anything else, Sebastian, you want to add?
No. I think that's all.
Perfect.